Good morning. My name is Vanshika from BSc Chemistry Honors final year. In this audio lecture for visually impaired student, I have taken a topic of photochemistry from Pradeep's book by Dr. S.C. Khetrpal. So let's start with introduction of photochemistry. Photochemistry is defined as that branch of chemistry which deals with the study of interaction of radiation with matter resulting into a physical change or into a chemical reaction called photochemical reaction, whose rates and mechanisms are studied after initiation by the radiant energy. Though the term radiation includes all types of electromagnetic waves from very low frequency microwaves to medium frequency infrared, visible and ultraviolet radiation to high frequency X rays and gamma rays, the radiation of photochemical importance are those which lie in the visible and ultraviolet region from 8000 to 2000 angstrom. Thus, the two main processes studied under photochemistry are: first is photophysical process, second is photochemical processes or photochemical reactions. So, first photophysical processes. Photophysical processes are those processes which take place in the presence of light but do not result into any chemical reaction. These processes arise on account of the absorption of light by the substances followed by the emission of the absorbed light. If the absorbed light is emitted instantaneously, the process is called fluorescence. If the absorbed light is emitted after some time lag, the process is called phosphorescence. Further, if the energy of the light absorbed is sufficiently high, the electrons may not only jump to the outer levels but may leave the atoms completely. The process is called photoelectric effect. Thus, photophysical processes include phenomena like fluorescence, phosphorescence, and photoelectric effect. Photochemical reactions are those reactions which take place by absorption of light by the reacting substances. These reactions are generally brought about by the absorption of light radiations of the visible and UV region, which lie between 8000 to 2000 angstrom, as already mentioned above. In these cases, the light energy absorbed is stored within the substance and then used for bringing about the reaction. A large number of different type of reactions can be brought about by exposure to suitable light. Example: synthesis, decomposition, oxidation, reduction, polymerization, isomeric change, etc. Two well-known examples of photochemical reactions are given below. First, combination of hydrogen and chlorine to form hydrogen chloride, that is H2 gaseous plus Cl2 gaseous. In presence of light, it is converted into 2HCl, which is gaseous. Second, photosynthesis of carbohydrates in plants taking place in presence of chlorophyll, the green coloring matter present in the leaves, and the reaction is 6CO2 plus 6H2O. In presence of light, it is converted into glucose, that is C6H12O6 plus 6O2. It may be pointed out that the photochemical reactions take place when incident photon has sufficient energy so that it can result in the excitation of one of the reactants from ground electronic state to excited electronic state. Example: Br2 in a mixture of H2 and Br2, as will be discussed later in this chapter. Difference between photochemical reaction and thermochemical reaction, or simply called thermal reactions. So the main points of difference a thermochemical reaction and a photochemical reaction are summed up like this. First point of thermochemical reaction: these reactions involve absorption of heat, but photochemical reaction, these reactions involve absorption of light. Second point of difference: They can take place even in the dark. Photochemical reaction take place in the presence of light. Third, temperature has significant effect on the rate of a thermochemical reaction. Temperature has a very little effect on the rate of a photochemical reaction. Instead, the intensity of light has a marked effect on the rate of a photochemical reaction. Fourth point is the free energy change of a thermochemical reaction is always negative. The free energy change of a photochemical reaction may not be negative. A few examples of photochemical reaction for which delta G is positive and still they are spontaneous are: first, synthesis of carbohydrates in plants; second, ozonization of oxygen; third, decomposition of HCl into H2 and Cl2. Fifth point of difference is in this thermochemical reaction, activation energy arises from the intermolecular collisions or it is supplied in the form of heat. In the photochemical reactions, activation energy is acquired by absorption of photons of suitable energy. Last point, when a reaction mixture is exposed to heat radiation, all the reactant molecules absorb these radiations and get excited almost to the same extent. That is, there is no selectivity. When a reaction mixture is exposed to light radiation, the molecules of one of the reactant may get excited independent of the presence of other species. Example, only Br2 molecule in a mixture of H2 and Br2. Now, laws governing absorption of light. So, when a monochromatic light consisting of a single wavelength is passed through a medium, some light is absorbed by the medium and hence the intensity of the incident light decreases. The decrease of intensity on passing through a pure homogeneous medium, that is a pure liquid, is governed by Lambert's law, and the decrease of intensity on passing through a solution is governed by a Beer's law. So first, Lambert's law. This law was put forward by Lambert in 1760. States as under: when a monochromatic light is passed through a pure homogeneous medium, the decrease in the intensity of light with thickness of the absorbing medium at any point x is proportional to the intensity of the incident light, that is the intensity of light at the point x, that is just before entering into the thickness dx. Mathematically, it is written as negative di by dx directly proportional to I, or minus di over dx is equals to ki, where di is the small decrease in the intensity of the light on passing through a small thickness dx. I is the intensity of the incident light just before entering the thickness dx, and the constant of proportionality k is called the absorption coefficient depending upon the nature of the absorbing medium. So the intensity I at any point x at a distance x from the start of the medium can be found in terms of the original intensity I naught as follows. So first equation can be written as di by I is equals to minus k dx. When x is 0, I becomes I naught, and when x is x, I is equals to I. Integrating this equation 2 between the limits x equals to 0 to x and I equals to I naught to I, we will get integration of between the limits I naught to I di by I is equals to minus k dx, or ln I by I naught is equals to minus kx, or we can write I by I naught is equals to e की power minus kx, or I is equals to I naught e e की power minus kx. So this equation expresses how the original intensity I naught is reduced to intensity I after passing through a thickness x of the medium. The difference between I naught and I obviously gives the intensity of the light absorbed. Thus I absorbed, that is intensity absorbed, is equals to I naught minus I, that is equal to I naught minus I naught into e की power minus kx. So the equation number 4, that is I is equals to I naught into e की power minus kx, can be expressed in another form which can be derived as follows. So 2.303 log I by में I naught is equals to minus kx, और log I by I naught is equals to minus k by 2.303x. log I by में I naught is equals to minus k dash x, और I by I naught is equals to 10 की power minus k dash x. So we can write this equation as I is equals to I naught into 10 की power minus k dash x. This is our equation number 7, where k dash is equals to k by 2.303 is called extinction coefficient of the substance, that is of the absorbing medium. Now it is this quantity which is called absorption coefficient or absorptivity of the substance. The physical significance of the extinction coefficient or absorptivity follows more clearly from equation number I by I naught is equals to 10 की power minus k dash x, which can be rewritten as k dash is equals to minus 1 by x log I by I naught, which is equal to 1 by x log I naught by I. And if log I naught by I is equals to 1 and k dash is equals to 1 by x, but log I naught by I equals to 1 means I naught by I is equals to 10, that is I is equals to 1 by 10 of I naught. Hence extinction coefficient or absorptivity may be defined as follows. The extinction coefficient or absorptivity is the reciprocal of that layer thickness expressed in centimeter at which the intensity of the light falls to 1/10 of its original value. Thank you. This is all about Lambert's law.